My dear students, good morning, and I welcome you all to this lecture on HVDC systems. Today we are going to start our module number 4. Okay, I'll write here module 4. This is the second last module. In this module, we are essentially going to study and understand control of HVDC link. You have an HVDC link and it is very important to control that link. We'll study what are the various control techniques, what are the control characteristics of an HVDC link. Before we study the control characteristics of HVDC link and the various methods of controlling of HVDC link, we must understand what should be what are the desirable features of control techniques. So first of all, I am going to discuss with you desirable control features. Desirable control features. So various desirable control features are: number one, control system should not be sensitive to normal variation. I will write here controller or control system should not be sensitive to normal variations in voltage and frequency. Voltage and frequency. You know, our system never has absolutely constant voltage. There are always voltage variations depending upon the load on the system, or there may be other causes of small voltage variations. Similarly, there may always be frequency variations within, of course, permissible limits. For example, if your system frequency is 50 hertz, it may be plus minus 0.5 hertz. I mean, sometimes it may go as high as 50.5 hertz and sometimes it may go as low as 49.5 hertz. Now, the frequency variation is because of mismatch. It is because of mismatch between generation and demand. Between generation and load demand, or I can say mismatch between generation and demand, which means that if generation is more than demand, okay, frequency will slightly increase. Say it may increase by 0.5 to 1 hertz, and if generation is less than demand, okay, frequency may slightly decrease temporarily. Or these variations in frequency are temporary. I mean, your frequency sometimes may go it may go from 50 hertz to 50.5 hertz, and sometimes if generation is less than demand, it may go down from 50 hertz to 49.5 hertz. So these are normal variations, small variations within the permissible limits, within the tolerance limits. And your controller should not be very sensitive so that it operates on these small or normal variations in voltage and frequency. So for small or normal variations in voltage and frequency, your control system should not operate. It should be very sensitive, but it should not be too sensitive to operate on normal variations in voltage and frequency. So which means it should be insensitive to normal variations in voltage and frequency. So this is the first desirable feature of your control system or controller. Second is your control system or your controller, or I should write control, should be fast, reliable, and simple to implement. Easy to implement or simple to implement. It should be very fast. Now, your controller comprises of two parts in your HVDC system. One is a controller which involves mechanical elements, and another is a controller which is purely electronic in nature. For example, the electronic control means controller with a converter control. It's electronic in nature. Converter control. The converter is controlled by delay angle control or firing angle control. That is, alpha is varied, alpha control is exercised. So by controlling the firing of valves of converters at the converting stations, a very fast control action will be resulted in. Okay. On the other hand, if control action is taken care of, or if control action is exercised through the operation of, say for example, online tap changing transformer, you have OLTC transformer, online tap changing transformer. This online tap changing transformer is mechanical in nature, and when an online tap changing transformer changes the tapping or it operates, it is slow or sluggish in response. So it is slow in response. So therefore, before the online tap changing transformer operates, your delay angle control is very fast and it operates before your OLTC transformer operates. Okay, so therefore the electronic control, that's converter control by alpha control, it's very fast and it is very simple to implement. So this is the other desirable feature of your controller. Third is, there should be, I will write here, there should be continuous operating range, continuous operating range from full rectification to full inversion, full rectification to full inversion, and vice versa, full inversion and vice versa. I mean, you are normally, if you have an HVDC system, say this is your one converting station and this is the other converting station. Well, this may act as a rectifier and this may act as an inverter. Okay, and there is power flow. This is the direction of current ID, and power flows in this direction from rectifier station to inverter station. That is true in that case where you are, this is the, for example, generating station. I mean, this rectifier station gets power from generating station, and on the inverter station you have a load center. It is connected to load center. So your rectifier station is connected to generating station and your inverter station is connected to load center. In that case, there is no possibility of this converter operating as rectifier and this converter operating as inverter, because you already know if this converter operates in rectification mode and if this converter operates in inversion mode, then direction of power flow will be reverse. I mean, power will flow from this converting station to this converting station, but that does not normally happen if this converting station is connected to generating station and this converting station supplies power to the load center. In fact, there was a query from one of the students from your group. I don't remember his name. It was a very genuine query. He was saying that this inverter, this converter, when we say that it is operating in inversion mode, basically its input still remains AC and its output is DC. I mean, in the inversion mode, this is the converter output voltage VDI, and this rectifier in the rectification mode, its output is VDR. So this is VDI, this is VDR. So if you see, if you analyze it, it still has input as AC and its output is, DC. Its output is DC. But when we say that it is operating in inversion mode of operation, that means you are basically transferring power from, power is not flowing from this end to this end. Power is flowing back. It is flowing from DC side to AC side. That's the only difference. Now, if you are this HVDC converter station is supplying a load center, okay, and then in that case, this is a two-terminal HVDC system. This two-terminal HVDC system can be realized only if you have, two buses. You have AC bus on this side and you have AC bus on this side also, which is possible only in case of an interconnected power system. In an interconnected power system, this can be a two-machine model. You can model this side as machine, this side also as machine. Then you have one bus here and one bus here. And then, the only difference between the normal two-machine model and this two-machine model is that your, DC, your transmission line in normal two-machine model is AC line. But here it is DC line, because you are converting AC into DC here, and here you are converting DC back into AC. But that is possible only if you have, AC side, already AC side is existing on this side, and you have AC side on this, okay? When this is also AC side, this is also AC side, then only we can say you operate this converter in inversion mode, and in inversion mode, power flows from inverter to this side. And then on this side you may have load centers and all that. But if you don't have an interconnected system, you don't have a bus, AC bus here, then there is no fun of having this inverter here. Then you can have simply this rectifier station, and then it will convert AC into DC, and then on the other hand you have to convert that DC back into AC by means of another inverter, which is not connected to AC bus, which is an inverter. But what this means, you have two machine model. You have AC side. This is you may have a rectifier here, rectifying station, and you may have an inverting station here. This is AC side. This is also AC side. Power flows from this to this. Okay. So in that case, this converter operates in rectification mode, and in this converter operates in inversion mode. When I say that this converter operates in inversion mode, it does not mean that it's converting this DC into AC and supplying that AC to load. AC is already there. What it does is that in inversion mode of operation, its voltage is VDI, which is same as VDR, and this power flows from this side to this side. You can say that this power which on this side is DC, it is converted into AC and fed to the load. Okay, but in actual practice, this is already an AC side is already there, and this AC side, if you see it in terms of converter operation, this AC is again converted into DC, just like the AC is converted into DC here. So it is very important to understand that if power has to flow from this end to this end, then this converter has always to operate in the rectification mode, and this converter has always to operate in the inversion mode. Now, under what circumstances power flow direction has to reverse? In this case, when this converter operates in rectification mode and this converter operates in inversion mode, power flows from rectifier station to inverter station like this, and it is then fed, maybe it is fed to the load center. Under what circumstances the direction of power flow has to change? The direction of power flow has to change if this is not generator, this is not load, if this is AC side, this is also AC side, and what we call as back-to-back HVDC system, back-to-back HVDC link. In back-to-back HVDC link, this is AC bus, this is also AC bus, and this converting station is at, say, region A, and this converting station is connected at region B. If you want power flow from region A to region B, suppose region A has surplus power and region B has deficient power, then power has to flow from region A to region B. In that case, this converter has to operate in rectification mode, and this converter will operate in inversion mode, and this is the direction of power flow. But sometimes you may be required to transmit power or transfer power from this region to this region. Say during certain period of time, this region may have surplus power and this region may have deficient power. So in that case, power should flow from surplus region to deficient region. So in that case, this inverter or this converter now has to operate in rectification mode, and this converter will operate in inversion mode, and direction of power flow will reverse. It will flow from this station to this station. So that is possible only if this is not connected to generating station and if this is not connected to load center. If this is connected to an AC bus, This is also connected to an AC bus. This represents region A, this represents region B. Power flows from region A to region B if this converter operates in rectification mode and this converter operates in inversion mode. And if the need arises, we can make this converter operate in rectification mode and this converter operate in inversion mode. In that case, power will flow from this region to this region. So that is called back-to-back HVDC link. Okay, so that's what I have written. One more desirable feature of controller should be that there should be continuous operating range for full rectification to full inversion and vice versa. Okay, this was third. Now fourth is control should be such that it requires less reactive power. Controller should be such that, control action should be such that your HVDC system requires less reactive power. Let me explain. I can explain it with the help of this diagram, schematic diagram of an HVDC power transmission system. This is a rectifier, or let us suppose this is rectification rectifier and this is inverter I. Okay, this is current ID and this is DC reactor, smoothing reactor LD. Now this is operated at certain the converters are operating at certain alpha. Okay, for power flow control, this alpha control is exercised. So if alpha is large, that means cos alpha is small and power factor will be poor. And poor power factor means, if power flows from this side to this side, there is the flow of active power. Your HVDC converter draws active power as well as it draws reactive power QA. Similarly, here power will flow from this to say load center, but reactive power will flow in this direction. So here you can see active power flows from AC side to DC side because this converter is operating in rectification mode and this converter is operating in inversion mode. So power always flows from rectifier to inverter, active power. And where does this reactive power flow? It will not flow through the DC line, because in case of DC there is nothing like reactive power. This reactive power is demanded by the converter because you are operating your converter at certain delay angle, and corresponding to that delay angle there may be certain power factor. If delay angle is large, power factor will be poor, and this converter will draw large reactive power for its operation. Similarly, on this side power will flow, on this side you have DC power, and then that goes to the AC side and that is fed to the load center L. Okay, but reactive power QA flows in this direction because this converter also operates at certain delay angle, and corresponding to that delay angle it demands reactive power. So reactive power is drawn by this converter as well as this converter. So therefore, in order to limit the reactive power, how do you compensate for that reactive power? You already have harmonic filters connected on the AC side here as well as here. Harmonic filters provide some sort of or some percentage of reactive power compensation, but not all reactive power compensation. So for providing all reactive power compensation, you have to use then reactive power compensators on the AC bus here as well as here. You have to use reactive power compensators. But you can reduce the demand of reactive power by these converters if you operate your converters at low delay angle. So alpha max is generally limited to 10 to 25 degrees only. You never operate your converter this at a delay angle more than 25 degrees, because if you operate it at a delay angle more than 25 degrees, higher the delay angle, lesser is the input power factor, and less input power factor means more and more reactive power will be demanded, and more reactive power means strong reactive power compensation has to be provided, which will add to cost of the system, and losses will also increase. So therefore, maximum delay angle in HVDC converter operation is just 10 to 25 degrees. We never operate our converter or rectifier at a delay angle more than 25 degrees. Okay, that was point number 4, desirable feature. And point number 5 is, I will write here, under steady state conditions. SS means steady state. Under steady state conditions, the valves must be fired symmetrically. I mean, if you remember, our valve firing is like this. Let us consider two valve conduction: 6 1 1 2 2 3 3 4 4 5 5 6, and then again 6 1. Here valve 1 is fired after 60 degrees, valve 2 is fired after another 60 degrees, valve 3 is fired after 60 degrees, valve 4 is fired after 60 degrees, 5 is fired, and after another 60 degrees, valve 6 is fired. So each valve is fired after 60 degrees. First 1 is fired, then 2 after 60 degrees, after another 60 degrees, valve 3 is fired, then 4 5 6. Okay, this is the firing sequence. So that means the valves are fired symmetrically at 60 degree intervals. So I will write here, valves are symmetrically fired at 60 degree intervals. So this sequence of firing is not changed even during mal operations. What are the various mal operations? You have studied various mal operations are arc through, misfire, and commutation failure. Even when this commutation failure occurs, even when this arc through occurs, even when misfire occurs, our controller should not change the sequence of firing. I mean, it was firing 1 here, then after 60 degrees, it should continue to fire 2. After another 60 degrees, it should continue to fire 3, then 4, then 5. Because, for example, if commutation failure is there, commutation failure may be there for 1 cycle, and by next cycle, this commutation failure will be over. And when it is over in the next cycle, normal operation will resume. And if by mistake you have, during the commutation failure, you have changed the firing sequence, I mean, you have increased the interval from 60 degrees to say 70 or 80, or you have decreased this, then when commutation failure is over, normal operation is restored, then since your valves are not fired symmetrically, so it will result in additional harmonics. For symmetrical firing at 60 degree intervals, the characteristic harmonics are there in the current drawn by the converters. Characteristic harmonics, you already know. What are the characteristic harmonics? H equal to NP plus minus 1, where N is integer 1, 2, 3, 4, P is the pulse number. For example, for 6 pulse converter, P equal to 6, N equal to 1, so harmonics are 5 and 7. Then for P equal to 2, P equal to 6, N equal to 2, harmonics are 11. I mean, for 6 pulse converter, the harmonics in the current drawn are 5, 7, 11, 13, and so on. And for 12 pulse converter, the harmonics are 11, 13, and so on. Okay, that means these are called characteristic harmonics. These are the normal harmonics. But if you change the firing sequence here during the faulty conditions, during the mal operations, if you change the firing sequence, then in addition to characteristic harmonics, interharmonics will also be there. Interharmonics are those harmonics which are other than characteristic harmonics, and interharmonics will increase the overall harmonic content in the current drawn by your converters, and total harmonic THD of the current will increase. So to avoid that situation, we always prefer to fire the thyristors symmetrically at 60 degree intervals, even during mal operations like arc through, misfire, and commutation failure. So this is next. Now next, this desirable feature, next desirable feature is that control should be such that, I will write here, control should be such that it controls the maximum DC link current or DC line current and limits the current fluctuation. Actually, what happens if this is your rectifier, this is inverter, if there is collapse of voltage on the inverter side, current ID is rectifier side voltage minus inverter side voltage divided by impedance. So current will increase. And if collapse of voltage is large, current may increase very high, and current may be so high that it may cause damage to both converters. All the valves may get, or most of the valves may get damaged, and your DC line may also get damaged. To avoid that situation, whenever this inverter side voltage collapses and current tends to increase, your control logic circuit or controller should act very quickly. Since it is electronic in control, what will it do? It should increase the delay angle of this, as well as it should decrease the delay angle of this, in such a way that in the worst case, the output voltage VDR should become 0, and VDI, that's the inverter side voltage, should also become 0. When the two voltages are 0, there will be no current in the link till fault condition is there. And when fault condition is, when the inverter side AC voltage is restored after a certain drop or dip, when it is restored, then normal operation will occur. So during the abnormal conditions like inverter side AC side voltage dip, the controller has to act very quickly. It has to exercise the delay angle control in such a way that rectifier side voltage also becomes 0. If inverter side voltage has collapsed, has become 0, rectifier side voltage should also become 0, so that current in the link does not rise to very large values. And this may be there for a few seconds or fraction of a second. When inverter side voltage is restored, okay, it comes back to its normal value, then normal operation will take place. So therefore, controller should take care of any increase in the DC line current by firing angle or delay angle control, and this control is very quick. And next requirement is that power should be controlled independently and smoothly which can be done by controlling the DC side current and or voltage simultaneously in the link. Let me try to explain it. The power in the DC link is given by PD is equal to VD into ID, DC side voltage or DC link voltage and DC link current. Okay, so you can control the power by controlling voltage independently, or by controlling current independently, or by simultaneously controlling voltage and current. But it is always avoided to have power control by simultaneous voltage and current control, because if you simultaneously control voltage as well as current, DC side voltage and DC side current, then your control action will be very complex. So to avoid the complexity, to make the controller easy, you either control voltage or current, and it is easier to control voltage rather than current, because voltage control is possible by alpha control. When you control alpha, you have studied AC to DC converters, phase controlled converters. By alpha control basically gives voltage control, and you have to maintain current constant. So DC line current is maintained constant, and it is easy to maintain DC line current constant and vary voltage. So therefore, DC link power or power in the DC link is equal to VD into ID. ID is maintained constant. So by controlling the voltage, the power control is achieved. Okay, that was about how to control the power. That was 7th, and therefore the last required desirable feature is control should be such that it can be used for protection of line and converter, for protection of DC transmission line or line and converter. See, if you have an AC system, for example, you have AC system. In case of AC system, you have circuit breakers, you have circuit breaker here, you have circuit breaker here. As soon as there is some fault in the line, etc., or on the buses, the circuit breaker quickly operates this or this circuit breaker and it isolates the line, trips the line. But we don't have circuit breakers in HVDC line. This is your HVDC line. You don't have circuit breakers in HVDC line. We don't have circuit breaker in HVDC line. So how to control this current? I mean, how to protect your converter and your line against short circuits? If a short circuit or fault occurs, okay, then control action should be very quick. So what is done? Alpha control, that is delay angle control, is exercised. And as I have already told you, if current goes very, very large, then alpha may be adjusted in such a way that the rectifier side voltage as well as inverter side voltage both become equal to 0. And when both voltages become 0, current temporarily becomes 0 in the DC line, or current starts falling to normal values. It's not allowed to rise to very high value till fault is cleared. Maybe within a fraction of a second, the fault is cleared and normal operation. So therefore, this control, alpha control, is used for protecting your line as well as converters against overcurrents due to short circuit or fault. Okay, so and this control is very, very fast. It's a quick control. So these are some of the desirable features. So I will just summarize what are the various desirable features. First desirable feature is controller should not be sensitive to normal variations in voltage and frequency, because there are always some small, within the tolerance limit, the voltage varies, the frequency varies. For small normal variations in voltage and frequency, your controller should be insensitive. It should not operate. Second desirable feature is there should be continuous operating range from full rectification to full inversion and vice versa. This is particularly true with back-to-back HVDC link. For back-to-back HVDC link, if power has to flow from region A to region B, then this converter should operate fully as rectifier and this converter should operate as inverter. And if power has to flow from this region to this region, then in that case, the roles of converters should interchange. Now, this converter should operate in the inversion mode and this converter should operate in the rectification mode. So this is true with back-to-back HVDC link. Third desirable feature is there should be continuous. Okay, second desirable range is control should be fast, reliable and simple to implement. Now your control comprises of electronic control and OLTC, online tap changing transformer control. OLTC control is mechanical in nature and slow in response, but your alpha control, converter control, is very fast and reliable also. And then next requirement, fourth requirement, is control should be such that it requires less reactive power. That means you have to limit the maximum delay angle to 10 to 25 degrees only, because by limiting the delay angle 10 to 20 or at the most 25 degrees, the reactive power requirement here is very, very small and you don't need large reactive power compensation equipments. Next is, under steady state conditions, the valves must be fired symmetrically, and this should be the firing sequence 1, 2, 3, 4, 5, 6. The valves should be fired symmetrically at 60-degree intervals equally, okay, even during the maloperations like arc through, misfire and commutation failure. This will ensure that there are only characteristic harmonics and there are no interharmonics in the system. The next desirable control feature is that control should be such that it controls the maximum DC line current and limits the current fluctuation. I have already told you, if inverter side voltage decreases, the rectifier's voltage remains same, the current may increase. To limit the magnitude of current, not to allow the current to go to very high values, okay, your controller, alpha control, has to be there, and your controller should act very quickly so as to maintain or decrease this line current so that it does not go to very large values. And then next requirement is, next desirable feature is, power should be controlled independently and smoothly by current control or voltage control or simultaneous current and voltage control. If you control power by voltage and current control simultaneously, then the controller will be very complex. Normally you have to control power either by voltage control or current control, and it is preferable to go for voltage control because your AC to DC phase control converters, whenever there is alpha control, that is delay angle control, it results in voltage, output voltage control, and you can maintain the current constant. So therefore power is controlled by controlling the average output voltage of the converter. Voltage control gives power control. And finally, your control should be such that it can be used for protection of line and converter. If a fault occurs, we don't have any circuit breaker, your alpha control should act very quickly, and it should reduce the rectifier side voltage, inverter side voltage also, such that in the worst case the two voltages are zero and current is not allowed to rise. And when the fault condition is over, normal operation begins. And to end my lecture, I again want to clear the doubt. If you are one doubt which is related to question asked by one of the students on the group way back, some 10-15 days back. I could not answer that question at that time because of some busy schedule. So if this is your HVDC system, this your rectifier station is fed from your generator, and you have then load here. I mean, if your system is isolated system, it's not an interconnected system, then on this side you have to have an inverter. You cannot have this type of inverter, phase control, line commutated inverter, because line commutated inverter basically is, again, it's basically AC to DC converter. Line commutated inverter always assumes that the rectifier or the inverter is always connected to AC side, grid or AC side, and then its output voltage reverses its polarity so that power flows from DC side to AC side. Otherwise, in rectifier, power flows from AC side to DC side, but in inverter, power will flow from DC to AC. That is what we actually mean by inversion. Inversion does not mean that your inverter is converting DC into AC. No, that's not possible. Okay, if your power system is an isolated power system, which is not the case in modern power systems, then on this side you have generator, on this side you have load. So, and if you want to transmit power from generator to load over HVDC transmission line, then what you have to do, this is your rectifier station, it converts AC into DC and power flows in this direction. Then you have to have an inverter here which will convert DC back into AC. And what type of inverter? It cannot be line commutated inverter, because line commutated inverter is basically thyristor converter which is connected with AC. You don't have AC, you have to create AC, you have to generate AC. Then you have to use some other inverter, like you may have to use this IGBT based inverter. Okay, maybe PWM voltage source inverter you have to use. And what an inverter does, an inverter has DC at its input and it converts DC into three-phase AC. And that type of inverter you have to use. And what about this? Here we are showing, this line commutated rectifier and line commutated inverter. This is true with those systems which are interconnected systems, because in interconnected systems you have AC bus here and you have AC bus here also. So both rectifier as well as line commutated inverter have inputs as ACs. So this is connected to AC grid. This is also connected to AC grid. Then this inverter, when we say that this converter operates in inversion mode, it does not mean it is converting DC into AC. It results in power flow from DC side to AC side. Or you can say that this power on this side is DC, and when it supplies power to load center here through this AC bus, it converts this DC power into AC power. But it does not convert DC voltage into AC voltage. AC voltage is already there. It is the grid voltage. So this you have to understand. It's very important. It is equivalent to have a two machine model. This is AC. You have already AC here. You have already AC here. Now what this rectifier station will do, it will take power from AC and that power will flow on DC. And what will this inverter, line commutated inverter, do? It will not convert DC into AC. AC is already there. What it will do, it will take DC power and it will supply DC power from converter to AC side. Okay. A rectifier takes power from AC and power flows from AC to DC, and in inverter power flows from DC to AC. So I hope this is clear. Now let us try to now we will discuss control characteristics of HVDC system. Control characteristics. Introduction. Our HVDC system is like this. Let us draw the complete electrical equivalent circuit of an HVDC system, which we have already developed in one of the earlier classes. This is VDOR cos alpha. This is rectifier side equivalent commutation resistance RCR. This is line resistance RL, transmission line resistance. This is inverter side commutation equivalent resistance RCI. And then this is your inverter voltage. And this is the tap changing transformer. What is this voltage? What is this voltage? This voltage is, you have written VDOR cos alpha, and this voltage is VDOI cos beta or cos gamma. Depends whether you are using beta or gamma. Okay, now this is DC line current ID. This voltage is VDR, this voltage is VDI, inverter average output voltage, rectifier average output voltage, and we know that DC line current is given by VDOR cos alpha minus VDOI cos beta or gamma divided by RCR plus RL plus minus RCI. Okay, plus sign is used for beta and minus sign is used for gamma. If you remember, because if you draw the equivalent circuit of inverter side in terms of beta, then your VDI is VDOI cos beta plus RCID. You have to go back to the equivalent circuit. Just recall what we have already done. And if your inverter, you are modeling this equivalent circuit of inverter in terms of gamma, then your inverter average output voltage will be VDOI cos gamma minus RCIID. In that case, this RC will be minus RC. That's what I have written here. It will be plus RC for beta and minus RC for gamma. Now, this is our, say, this is how control is achieved. Let us suppose this is the commutation voltage of value 3, 0, pi. And this is alpha, this is U, and this is gamma. And U plus gamma is beta. So beta is equal to U plus gamma. Now you can have two control parameters. You can take beta as control parameter for inverter control. For rectifier control, the control parameter is alpha. For inverter side control, you can have beta as control parameter. Beta can be treated as control parameter. Or we can have gamma as control parameter. Now what is the problem if you have beta as control parameter for inverter? I will write here for inverter side. For inverter, if you have beta as control parameter, the problem with beta control is that your beta is U plus gamma. Suppose U increases. When U increases, gamma automatically decreases and gamma becomes less than gamma min. And what is your gamma min? Say 10 to 15 degrees. If it becomes less than gamma min, commutation failure will occur. This will result in commutation failure. We already know. We have already studied. We have drawn the waveforms also for this. So therefore, one way of avoiding this commutation failure is increase beta. Can you increase beta? Because if you increase, earlier your beta was only there. If you increase beta, so that will increase U. The U has already increased, that will increase gamma also, because beta is equal to U plus gamma. What happened? Because of some faulty condition, U increased, gamma decreased because beta is constant, so gamma became less than gamma min and it resulted in commutation failure. You can avoid commutation failure by, if your controller increases beta, because if it increases beta, gamma increases and gamma becomes greater than or equal to gamma min, and that will avoid commutation failure. But the problem with beta increase is that it will increase the harmonics in the currents which are flowing on the AC side of the converter. Just like you increase alpha, I mean when you increase alpha on the rectifier side, this is your rectifier side. When you increase alpha, it draws more and more harmonic currents. On the inverter side, if you increase, on the inverter side here, if you increase beta, so this inverter will also draw more and more more and more harmonics and more reactive power. So if you increase alpha here, it will draw more reactive power. If you increase beta on inverter side, your converter will draw more reactive power. Okay, let's forget about harmonics. Let us talk in terms of reactive power. You have just now seen alpha increase means cos alpha decreases, so more reactive power is drawn by this rectifier. Similarly, on the inverter side, if you take beta as control parameter, and to avoid commutation failure, if beta increases, if controller increases beta, increase in beta means your converter is drawing more and more reactive power, QA, and that is a problem. So therefore, beta control is not a feasible way. It cannot be taken as a control parameter. Therefore, what is practically done by the controller? Gamma is always taken as control parameter. And when gamma is taken as control parameter, it performs gamma control. And gamma acts in such a way that gamma is never allowed to go beyond less than gamma min. Gamma never goes less than gamma min. Gamma is always maintained either greater than or equal to gamma min to avoid commutation failure. So therefore, a type of control which is called constant extinction angle control is exercised. So on inverter side, we have constant extinction angle control. Constant extinction angle control. Extinction angle, that is CEA. C for constant, E for extension, and A for angle. CEA control. What this CEA does, constant extinction angle control, the inverter, it always maintains gamma constant. And it is maintained constant at gamma min. So that even if the commutation failure occurs, gamma is not allowed to go below gamma min, and commutation failure is always avoided. So commutation failure is avoided. Now, therefore, now you have two sides. You have rectifier side and you have inverter side. Generally, the control action is such that on the rectifier side, we have current control, constant current control, and on the inverter side, we have constant extinction angle control. So therefore, rectifier side, if you take, on rectifier side, we have constant ignition angle control. Constant ignition angle, CIA control. Because alpha has to be less than or equal to alpha max. You never allow alpha to go greater than alpha max, because if alpha goes greater than alpha max, it draws more and more reactive power. So that's called constant ignition angle control. Alpha is varied on the rectifier side, but it is not allowed to go beyond alpha max. So that control is called constant ignition angle control, CIA. Ignition angle, in the days of mercury arc rectifiers, this delay angle was called ignition angle, but this terminology has not been taken out. This terminology is still used. Although we don't have now ignition angle, we have firing angle or delay angle, but it is still called ignition angle control. And on the inverter side, we have constant extinction angle control. Constant extinction angle control, that is CEA control. So there gamma is always maintained constant at gamma max. So it is constant to avoid the possibility of commutation failure. One more thing now, with this you can now draw the characteristics, control characteristics. This is DC line current versus DC side voltage, VD, ID versus VD. Now your rectifier characteristics, VD versus ID, will be like this. It will be like this. This is called constant ignition angle control, CIA control. And this is true for rectifier. And what about inverter? For inverter, you have, and then for rectifier, you have constant current control also. This is called constant current control, CC. because here you can see current is constant. There is large variation in the voltage, but current is maintained constant. And for inverter, this is the type of control. This is called constant extinction angle control, CEA control. This is true for inverter. So for rectifier side, we have constant ignition angle control plus constant current control. And for inverter side, we have constant extinction angle control, CEA control. Now we can see the slope of rectifier control characteristic is more than that of inverter. That is because of the reason that if you find the rectifier voltage, if you find the rectifier voltage VDR, that is equal to VDOR cos alpha minus RCR plus RL into ID. And for inverter, VDI is equal to VDOI cos beta or cos gamma minus RCIID. On the rectifier side, when you find the rectifier average output voltage, this is maximum, this is VDOR cos alpha, that is average output voltage of the converter, minus voltage drop in the line, transmission line, and voltage drop because of equivalent commutation resistance, because of overlap angle. So these two. And for inversion, it is equal to inverter average output voltage minus current into equivalent commutation resistance of inverter. Here it is RCR plus RD. So therefore this drop is more than this drop. So therefore slope of rectifier characteristic is more than the slope of inverter characteristic. And the point of intersection is here. This point of intersection, it gives the operating point. This is the operating point of your HVDC link. Operating point of HVDC link. Your HVDC link operates here. Now, the problem with this is the rectifier characteristic. It comprises of constant ignition angle control plus constant current control. And this is the inverter characteristic, VI characteristic. This is called constant extinction angle control, CEA. And the point of intersection gives the operating point of HVDC link. So your HVDC link, when it operates, the voltage of the link will be this much and current will be this. But the problem with this characteristic is that suppose the rectifier side voltage falls. Suppose there is your rectifier is connected to AC side, and if there is a sag or dip in the AC side voltage, so rectifier output voltage also falls. If it falls from this value to this value, okay, it falls. There is still then it has this CIA characteristic control, and then it has CC control. You still have operating point at this. But if rectifier characteristic falls below this inverter, so this is your rectifier characteristic, CIA plus CC, and this is inverter characteristic. The two characteristics are not intersecting each other. Here the rectifier characteristic and inverter characteristic, they are intersecting, and this is the operating point. If rectifier side voltage dips, still you have point of intersection. This is the operating point. But if rectifier side voltage dips, there is a deep sag or dip in the rectifier side voltage. It may dip below the inverter characteristic, and then this is rectifier characteristic, this is inverter characteristic. The two characteristics are not intersecting with each other. So in that case, there is no point of intersection, no operating point. So for this, there is no operating point. No operating point means your HVDC link will not supply any power. No power transfer will take place from AC side to DC side. So to avoid this situation, what is done? This characteristic VI, characteristic or control characteristic of your HVDC link is modified like this. This is ID and this is VD. Okay, this is a rectifier characteristic which comprises of constant ignition angle control and constant current control, CC. And then this is the inverter characteristic. It has less slope. This is inverter characteristic which comprises of constant extinction angle control, and it also to the inverter characteristic also constant current characteristic is given. Okay, otherwise initially the inverter characteristic was only comprising of CEA control, not CC. But to avoid this situation where there is no operating point, no point of intersection, inverter is also given constant current characteristic, so that if this voltage falls, you have this as point of intersection. If it further falls, you still have this point of, if voltage falls deeply, rectifier side voltage falls deeply, then this is rectifier side characteristic and this is inverter side characteristic. The point of intersection is here. So you still have point of intersection, and you will, even if the rectifier side voltage falls very, very deep, you always have point of intersection between rectifier characteristic and inverter characteristic, and this will always give the operation of the HVDC link. HVDC link will not lose the power, it will not lose the control, it will always supply power. No doubt in this case it will supply less power, but power will be always supplied. So this is the modified characteristic of your HVDC link. So therefore your HVDC link control characteristic comprises of control characteristic. It comprises of, let us first of all take rectifier. Rectifier has two characteristics: CIA, that's constant ignition angle control, plus CC, constant current control. That is this, CIA plus CC. And inverter also has two characters: constant extinction angle control, CEA plus CC. Constant extinction angle control plus CC. Okay, so this is about HVDC link control characteristics. Now let us discuss now effect of AC side voltage on DC link current. Whenever there is AC side voltage change, whether on rectifier side or inverter side, the DC link current changes, and your HVDC controller is such that it has to always maintain DC line current as constant, as I have already told you. What is aim of controller? To keep DC line current ID always constant. Always constant. Now the situation is like this. This is your rectifier station and this is rectifier. Okay, and this is DC line inductor LD, DC line current ID, which has to be maintained as constant. This is inverter side. This is line commutated inverter here, and this is its AC side. Okay, now this is VDR and this is VDI, and we know ID is VDOR cos alpha minus, we already know that this DC line current is VDOR cos alpha minus VDOI cos beta divided by RCR plus RL minus RCI. Okay, if if gamma control is taken, this is cos gamma here, not cos beta. Now why cos gamma? Because gamma is our control parameter on inverter side, control parameter. On rectifier side, alpha is the control parameter. On inverter side, we have gamma as control parameter. Gamma is always maintained constant at gamma min. That's called constant extinction angle control, CA control. Now, let us see the effect of change in the voltage. Number one, increase in rectifier and AC voltage. Let us assume that due to some problem, the rectifier side AC voltage has increased. This voltage has increased. Now, when this voltage increases, the VDOR, rectifier side voltage, is equal to 3 root 3 EM by pi. You already know rectifier average output voltage is 3 root 3 EM by pi into cos alpha. This is 3 root 3 EM by pi cos alpha. So this is VDOR is 3 root 3 EM by pi. If rectifier side AC side voltage increases, that means EM increases, that increases VDOR. And when VDOR increases, VDOR into cos alpha also increases. So therefore what will happen to ID? ID, which is equal to VDOR cos alpha minus VDOI cos gamma divided by RCR plus RL minus RCI. Since rectifier side AC side voltage has increased, EM has increased, that means VDOR has increased, so this will increase. So what will happen to DC line current? It will increase, but your controller has always to maintain your DC line current constant. So how can controller maintain DC line current constant? What is aim? Aim is to maintain DC line current constant. ID should be equal to ID ref, reference DC line current, constant. So now in this case, what has happened? ID has gone greater than ID ref. So controller will very quickly act and it will try to reduce ID. How it will try to reduce ID? By increasing alpha. So alpha will be increased. Alpha is the delay angle. So when alpha increases, that decreases cos alpha. And when cos alpha decreases, so this VDOR cos alpha, VDOR has increased, cos alpha will decrease. And this VDOR into cos alpha, ये वापस आ जाएगा normal value पे, and ID will be equal to ID ref. Now let us suppose take a case where your controller is increasing alpha, but it cannot increase alpha beyond 20 or 25 degrees. What is maximum delay angle? 20 to 25 degrees. Let us suppose it has taken alpha to 25 degrees. And when alpha is 25 degrees, it cannot take it beyond 25 degrees because the alpha max is only 25 degrees. Let us suppose VDOR cos alpha is still increased. I mean, increase in VDOR is more than decrease in cos alpha. So current will still be greater than ID ref. ID will be still greater than ID ref. So what will your controller do? Online tap changing it will operate. You have online tap changing transformer here. So it will change it will operate online tap changing so that your transformer goes to lower tap. When it goes to lower tap, what will happen? The input voltage will decrease. Okay, because there was increase in input voltage will decrease. OLTC on rectifier side will operate. So what will this do? This will decrease EM, input voltage. So that will decrease VDOR. So when VDOR is decreased, it is possible that now VDOR cos alpha has come back to its normal value and ID is equal to ID ref. Now let us suppose your online tap changing transformer has decreased VDOR, but still ID is greater than ID ref. I mean, I am taking the extreme case, worst case. In that case, what will happen? That means rectifier side online tap changing has also failed. Now we have inverter side online tap changing. Now inverter side online tap changing will operate. What will it do? It will increase voltage of this inverter side. So inverter side online tap changing will operate. It will increase inverter side voltage because your current is rectifier side voltage minus inverter side voltage. Inverter side, when it increases inverter side voltage, so current will decrease, and current decreases till ID becomes equal to ID ref. So therefore, I repeat, if there is a voltage swell on AC side of rectifier, AC side voltage has increased. Maybe some ground fault has occurred, and ground fault always increases the voltage. When rectifier side AC side voltage has increased, the current has increased because VDOR has increased. So now your controller has to maintain current always constant at ID ref. So controller will quickly act. It will increase the delay angle of this rectifier so that cos alpha decreases and VDOR becomes equal to VDOR. But if VDOR so that ID becomes equal to IDR, but ID ref. If ID is still greater than ID ref, then online tap changing here will increase. It will decrease the tapping of this, decrease the voltage, and ID will become equal to ID ref. But if that also fails, then inverter side or online tap changing will operate. It will increase the tapping of this transformer so that VDI increases. When VDI increases, the current is this voltage minus this voltage by resistance. So ID decreases, and it is possible now that ID becomes equal to ID ref. So therefore, this is the sequence of actions which will be taken by your controller to maintain ID equal to ID ref constant. Now next is decrease in rectifier side rectifier and AC side AC voltage. Decrease in rectifier and AC voltage. Now suppose voltage dip has occurred. Voltage dip can also, a fault has occurred on the AC side of rectifier, that is called voltage dip. When dip has occurred, what will happen to VDOR? VDOR is 3 √3 m by pi. EM will decrease. VDOR is equal to 3 √3 EM by pi. If voltage dip on AC side of rectifier has occurred, this has decreased. This has decreased VDOR. Your DC line current is VDOR cos alpha minus VDOI cos gamma divided by RCR plus RL minus RCI. So since this has decreased, current will decrease and ID will become less than ID ref in this case. Now your controller will very quickly act. What will it do? It will reduce delay angle of your rectifier, okay, converter. So it will reduce, controller will act now. What will controller do? It will reduce delay angle. But what is the minimum delay angle? Minimum delay angle is 5 degrees. You cannot go below 5 degrees. I have already explained in one of the early lectures. Okay, one of the preliminary lectures, I have explained that minimum delay angle cannot be less than 5 degrees. Let us suppose it has already taken alpha to 5 degrees, but this cos alpha will increase. But let us suppose this VDOR is decrease in VDOR is still greater than increase in cos alpha. So ID is still less than ID ref. ID has increased, but it is still less than ID ref. Now what will happen? The rectifier side on-line tap changing will operate. When it operates, it increases the tapping of transformer so that the voltage, already dip had taken place, so the voltage on the AC side will increase. Okay, so what will now have, what is the next control action? If this first control action fails to make ID equal to ID ref, ID is still less than ID ref, next control action is rectifier side online tap changing will operate. It will increase EM. Okay, so that will increase VDOR. Okay, so but if VDOR has increased to sufficiently large value, then ID will be equal to ID ref. But let us suppose VDOR is, increase in VDOR is not sufficient. So ID will still remain less than ID ref. Then what is the last? That means this control action has also failed. What is the last control action that controller has to take? Online tap changing of inverter side has to operate. Now since ID has become less than ID ref, ID has to increase. That is possible only if this VDI decreases. That is possible if online tap changing of inverter side transformer decreases its tapping. When it decreases its tapping, VDI decreases. Okay, so VDOI decreases, so VDI decreases, so current increases, and it is now possible that current will become equal to ID ref. This is the sequence of control action. Now third is, first was increase in rectifier side AC voltage, second was decrease in rectifier side AC voltage. Now same problems may occur on the inverter side. Now we will take third possibility, that is increase in inverter side AC voltage. Let us suppose inverter side AC voltage has increased. Okay, some fault has occurred here that has increased inverter side AC voltage. What will that do? That will increase this VDOI cos gamma. So ID is equal to VDOR cos alpha minus VDOI cos gamma divided by this. So since this inverter side voltage has increased, current will become less than ID ref. So ID will become less than ID ref. Now your controller has to operate. Now what will your controller do? Your controller can decrease gamma. If it decreases gamma, if it decreases gamma, cos gamma increases. Cos gamma increases. It has to increase gamma. If it increases gamma, cos gamma decreases. And there was increase in this VDOI, cos gamma decreases. So it will bring this VDOI into cos gamma to normal value. But the problem is that gamma cannot be increased or it cannot be decreased also, because on the inverter side we have constant extinction angle control, CEA. Constant extinction angle control means the gamma is always maintained at a constant value, gamma min. It is neither increased nor decreased. So therefore the possibility of gamma control, gamma increasing is not possible. Gamma is always maintained at a constant value, that is gamma min. So what is the other possibility? Rectifier side controller will operate. It has to increase the current. So it will decrease alpha. So on the rectifier side, alpha decreases. When alpha decreases, VDOR cos alpha, it increases. That increases current, and it is now possible that current is become equal to ID ref. But if current has not become equal to ID ref, you may say it may further decrease alpha, but alpha max is 5 degrees. Let us suppose it has already reached this minimum threshold, 5 degrees, and ID is still less than ID. ID is still less than ID ref. Then what will happen? rectifier side, this online tap changing will operate. It will increase that tapping. Online tap changing on rectifier side will operate. It will increase VDOR, and it is now possible that ID has become equal to IDREF. But if ID is still less than IDREF, then inverter side online tap changing will operate. That will decrease this inverter side tapping, and so that VDOI decreases and ID increases, and it is now possible that ID becomes equal to IDREF. I am considering extreme cases. Otherwise, this alpha control itself in the first control action is alpha control. When alpha control is done, alpha is decreased, the current is increased, and in the first control action itself, ID will become equal to IDREF. But if that does not happen, okay, then rectifier side online tap changing will operate. It will increase the rectifier side voltage VDOR, and ID will increase. And in that case, ID will become equal to IDREF. But if the extreme case is taken, ID still is not equal to IDREF, then inverter side online tap changing will operate. That will decrease the tapping of inverter transformer, and inverter side voltage VDI will decrease, and current will increase, and finally current ID will be equal to IDREF. So the last is, so fourth is decrease in inverter side AC voltage. I mean, inverter side AC voltage has decreased now. This is your inverter side AC voltage. Some fault has occurred here, that is called voltage sag or voltage dip of the AC voltage on the inverter side. So because of that, what will happen? VDOI, which is equal to 3 root 3 EM by pi. Since inverter side voltage has dipped, EM will dip, VDOI will dip. And what is your ID? ID is equal to VDOR cos alpha minus VDOI cos gamma by RCR plus RL minus RCI. Since inverter side voltage has dipped, VDOI has dipped, so what will happen to current? Current will increase and it will become greater than IDREF. So controller will now quickly come into action. What is the first control action controller would have taken? It would have reduced gamma. Gamma reduce karta, so cos gamma increase hota और ये product वापस अपने normal. But gamma it cannot, because gamma is your inverter side. Inverter is operating at constant extinction angle control, CEA control. So gamma is always constant. Gamma is equal to gamma min. So gamma control is not possible. So what it will do? Controller will it has to increase. It has to decrease current. It will increase on rectifier side. It will increase alpha. When it increases alpha, cos alpha decreases. उससे क्या होता है? ये product decrease हो जाता है. VDOR cos alpha decreases और आपकी current कम हो जाती है. It is possible that when current decreases, ID is equal to IDREF और control action खत्म. But if इसने alpha increase किया, what is the maximum alpha? Maximum alpha is 20 to 25 degrees. Suppose it has already reached maximum delay angle. It cannot increase beyond this. Controller will not allow it to go beyond 25 degrees. And let us suppose at alpha equal to 25 degrees, alpha max equal to 25 degrees, ID is still, greater than IDREF. ID has decreased, but it is still greater than IDREF. And what will happen? Rectifier side online tap changing will operate. So on rectifier side online tap changing, what will it do? It has to decrease current. It will reduce the transformer tapping. So उससे क्या होगा? VDOR will decrease. उससे ये होगा, when VDOR decreases, this product decreases and your current decreases. And when current decreases, it's possible that ID is equal to IDREF. But if ID is still not equal to IDREF, let us suppose ID is still greater than IDREF, the inverter side OLTC will operate. What will it do? It will increase. इसको करंट कम करनी है. I mean ये करंट कम होनी चाहिए. That means inverter side output voltage should increase. It will increase its tapping. When inverter side online tap changing occurs, it will increase the tapping. So VDOI increases. So VDOI increase होने से क्या होगा? VDOI cos gamma भी increase हो जाएगा. ये product increase हो जाएगा. So ID will decrease. And now it is possible that ID has become equal to IDREF. So this is how your controller operates to various, problems. If rectifier side input voltage increases, if rectifier side input voltage decreases, or if inverter side input voltage increases or inverter side input voltage decreases, then this is how controller operates. Controller takes very quick action. First, electronic action, alpha control. If alpha control fails, then online tap changing control, and it always maintains ID equal to ID ref, constant DC line current. So with this, I will end my today's lecture. More on it in next lecture. Please go through this lecture. Try to study these control characteristics of your HVDC link. And in case of any doubt, you are free to ask me. I will be happy to clear your doubts. Thank you.